being 60 days late. It's a very simple concept on sensitivity analysis. We normally change one variable at a time and see how sensitive lifecycle profits is to each one. And we get out an output that looks like this. 1% expense overruns worth $40,000, 1% cost overruns worth $150,000, 1 month delay is worth $500,000. And that then brings everything into the same unit of measure. And now we can start making decisions in a sort of fact-based way instead of in a qualitative way. So what do I mean by the qualitative way? Well, you see some companies saying, oh, I need to have more money to accelerate the development of this product. Marketing says we need this product earlier, so we need to reduce the cycle time on the project. And this is one of our strategic objectives for the year. And then manufacturing says, you know, we have another strategic objective, which is to lower our product cost. So you should give me money to lower product cost, because that's a strategic objective too. And then it becomes a battle of eloquence of who can most best represent their strategic objective. What we like to see happen is it to turn into a quantification of the benefits of things. So when manufacturing says, give me 2 months of extra cycle time so I can lower the cost of the product, I can say, how much will you lower the cost of the product? By 2%? Well, 2% is worth $300,000. 2 months of cycle time is worth $1 million. I do not want to trade $1 million of cycle time for $300,000 of product cost. If they say we can lower product cost by 20%, that's worth $3 million. That is a good trade-off. And so it's not what is your favorite objective, what's our priority on this program, speed or cost. Our priority is overall life cycle profits. We trade off these things against one another based on their actual value in a particular situation. And you do that with an economic model. Normally, people, let's see if I have that slide. I did, okay? So I don't know how many slides I put in this deck for a short speech. So a lot of people agonize over, you know, well, can I really calculate cost of delay accurately to 3 significant digits? Because it would not be useful if I could not do an accurate calculation. The point I always make to people is your competition is not the perfect answer. Your competition is how do you make decisions that affect cycle time today. And I'll give you a very simple exercise you can do on any one of your projects to illustrate sort of what people, because today most people use their intuition. 85% of developers use their intuition on cost of delay. And the simple test I like to ask people to do is gather 10 people in the room who are all in a position where they could delay the project. They play a role on the critical path of the product development. And ask those people, what would it cost our shareholders in terms of life cycle profit if this program was delayed by 60 days? And I tell them, write that number on a piece of paper. We are going to rank them from the highest to the lowest number that we get within the group. Now, the typical range, and I started doing this 30 years ago when people would say, I prefer not to use quantification. I like to use my intuition because we've been in this business for 50 years and we have highly developed intuition. I said, okay, I'll accept that. Let's see how highly developed your intuition is. The typical range I get with intuition is 50 to 1. And I hope that should disturb you, because that means that some people are paying 50 times as much for the same week of cycle time as other people. And they believe they are doing the right thing for these organizations. These are smart people who are acting responsibly in good faith to try to make good decisions. It's just their beliefs about what cycle time is worth differ by 50 to 1. And as a result, you've got chaotically different decisions being made within the same development program. The minimum range I have ever seen with intuition is a 10 to 1 range. Poor intuition, actually, I don't have space to show poor intuition. Poor intuition occurs when one person in the company will say, it will cost us £200,000 a month if we're late. And somebody else who is usually going to be an engineer, because engineers have less social skills than marketing people. So usually the engineer says, you know, I really don't think it's going to cost us a penny because nobody's going to buy any of these anyway. And so the Guinness Book of Records is infinite range in cost of delay. I've seen that happen more than once. I've seen it happen with very famous British companies had an infinite cost of delay when I discuss things with them. So, and interestingly, when you do an analysis, routinely people will get a 2-to-1 range on the analysis. We went through a example in the course today, and things where we took just some random spreadsheet data. It wasn't completely random; it was pre-planned, but we had people do a cost delay analysis, and they made radically different assumptions, and they got about a 5-to-1 range in the answer. And that's better than the best you would see with intuition on the first try. The first try they ever did in doing cost delay, they were better than the best intuition that ever produced. And that's why it's such an important idea. Okay, here's an example on Boeing, what they did with an economic model. Boeing had when they were doing the Boeing 777, the plane was overweight. They had performance penalties they would pay if the plane was overweight. They would pay the excess fuel consumption for every plane United Airlines bought for the entire flying life of the plane. And when they did a weight roll-up, the plane was overweight, and they said, we're going to lose hundreds of millions of dollars. We need to do something. They came up with an interesting approach of every engineer can buy weight for $300 a pound. If you can do a material substitution or a design change that removes a pound of weight for less than $300 impact on unit cost, you have immediate permission to do that. This then had 5,000 engineers operating with no adult supervision, making weight changes on one of the most critical performance parameters on that plane, and it brought the plane in on its target weight. And I say, what is the difference between this and what they have traditionally done? What they traditionally had done is nobody had ever told an engineer what a pound of weight was worth. So even though they told the engineers weight is important, they never told them what it was actually worth at a system level. So you had people buying weight for totally different prices in different areas on the plane. There was no consistency in the way they were doing it. The brilliant thing about this is a system level optimum trade-off rule calculated by the program manager who has a system level view of the problem, and therefore you had 5,000 engineers making system level optimum decisions instead of doing local optimization on their individual piece. And it was because somebody took the time to get the right information in the hands of the engineers. Is that if you don't provide the right information, even smart, motivated people will not make the right choices. Okay, so product development, we always make the trade-offs between multiple objectives. Anytime we have more than one moving part, we have to use quantification. This quantification is usually to a useful level of accuracy. It's surprisingly easy to do, and it supports the idea of decentralizing decisions when you give people, when you don't give people the right information to make decisions, and all you do is flow down authority, they will make random decisions, and you will say, what a stupid decision you made. I never should have decentralized authority in this organization. When you give them the correct information to make decisions, because the bad decisions don't result from stupid people or bad intent. They result from not having the right information to make decisions. And when you put the right information down, you get the good decision, and then you say, decentralization really works. Okay, second big idea is invisible, unmanaged queues are the root cause of poor economic performance and product development. This is the queuing system I always use to explain queuing to people. I say, traffic at rush hour on a crowded highway. If you take what I come from California, so we would call this a 4-lane highway. Here you would call it an 8-lane motorway. But if you remove 1 lane from a 4-lane highway at rush hour, you are removing 25% of the capacity. What happens to cycle time? Does it change by 25%? No, you double or triple cycle time. What happens when you remove a lane of capacity at 3 a.m. in the morning? Nothing happens. Anyone who has ever been in rush hour traffic intuitively understands the way queuing systems work. That the time in the queue depends on changes in the cycle time depend on the level of loading. And as you change the level of loading, the queue goes up non-linearly, and it depends non-linearly on the capacity utilization. And this is real queuing theory. This is an MM1 infinite queue. It's one of the types of queues you have. The important thing about this queuing curve is the way it rises geometrically at the end. The closer you get to 100% utilization, the more the denominator ends up approaching 0, and this queue goes up to infinity. And so management's desire to load to 100% utilization is actually undermining cycle time in our process. One of the most dangerous beliefs that management has is the higher I make utilization. If I make utilization really high, then nobody is wasting their time. And if nobody wastes their time, then I'm going to have a really productive process. I will maximize output. The reality is when nobody is wasting their time, queues are at their maximum size. So the resources are not wasting their time, but the work product is sitting idle, waiting on the critical path to access the resources. And the real economics of product development looks more like this. I have 2 cost components. One is excess capacity. The other is the cost of delay. They are both present. The more I reduce the excess capacity, and I can make a set of these slides available to Darren and things like that if you want it. You don't have to try to take pictures and copy.
It was fun watching you do this.
I'll just eliminate some of it. Because there's a little too much content I'm trying to go through to make it easy to both listen and compensate. But what's going on here is as I drop the amount of excess capacity in the system, the queue gets larger and larger. When the queue is on the critical path, it generates a cost of delay. So I was working with one company. They said, we really made a smart decision in our engineering drawing section. We bought 5 seats of Pro Engineer, and they are utilized from 5 a.m. in the morning till 5 p.m. at night. So we must have gotten the right amount of capacity. And I said, you know, there's another way to look at this problem. Why don't we make a list of everything that is waiting to get into engineering drawing right now? And why don't we calculate for items that are on the critical path, what is the cost of delay? How much money are we throwing away by having valuable work products standing in line and not progressing towards the marketplace? I showed them they could have bought 10 times as many seats of Pro Engineer for the money they were throwing away in the queue than what they had ended up buying, because they had created this massive queue in their process. Now, the interesting thing in the world, I would say, is that most people only see the green line. In most organizations, they are only aware of the cost of capacity. They are not aware of the cost of the queue. And for 2 reasons. One is only 15% of organizations actually know the cost of delay on the major projects they're working on. So 85% of the world doesn't even have a clue what the cost of delay is. And you need to know cost of delay to know what the cost of the queue is. But even worse, only about 2% of organizations are measuring the size of queues in their process, because queues in engineering are invisible. And queues are information. Our work product is information. Information is invisible. People do not believe there are queues in engineering. They believe there are queues in a factory because they see big piles of work on the factory floor. They believe there are no queues in engineering because they don't see any. So they don't measure queues, they don't see where the queues are, they can't draw this red line. So they live in a world where there's only one cost, it's the cost of excess capacity. They want to be as close to full utilization as they can, and that just creates an economic disaster for most organizations. And I would say, I'd say they're correct in believing that excess capacity is a form of waste, but when you try to optimize a system, you do not locally optimize only one form of waste. There are two forms of waste in this process. One is the engineer being idle part of the time. The other is the work product being stationary, waiting to access a resource. And what this graph is telling you is when you have very low waste in the engineering, the busy engineer side, you've got massive waste on the part of your product waiting in line, trying to get through the system. Okay? And that's what we're trying to fight with some of these things. So what do we think about managing queues? Most people think, most organizations think that high utilization is good in a product development process. It's completely the opposite. They don't measure their queues and often don't even believe they have queues because they're invisible. That causes them to underestimate the true cost of overloading their processes. The overloads hurt all dimensions of product development. They hurt cycle time, they end up hurting quality because they delay feedback in processes, they hurt the efficiency of a process. And so one of the easiest ways to damage a product development process is to create large queues in the process. That's very dangerous for product developers. Third big idea. In product development, we should try to alter the economic impact of variability rather than trying to eliminate it. And to show you this, I need to dip into a little bit into financial theory, which not all of you will have been exposed to, but I'll give you a pretty simple explanation. It's back in the 90s, Robert Merton and Byron Scholes won the Nobel Prize in economics for doing the Black-Scholes option pricing model. The first time people had rigorously quantified the value of the stock option. And a simple but pretty accurate example of how options work. I've got three graphs here on this page. The upper right-hand graph is what we call the payoff function. And this is telling me how much money I make from an option as a function of the price level of the stock. So an option gives me a right to buy a stock at a strike price. Let's say I've got a right to buy Apple stock, on the 15th of July at $140 a share. If the actual price on the 15th of July is below $140, I will not exercise the option because I can buy that stock on the market for a lower price than I can buy it with the option. What that means is anytime the price is lower than the strike price, I let the option expire worthless. Anytime it is higher than the strike price, I put an extra dollar in my pocket for every dollar it's higher. Now, to know whether you're going to make money on an option, you need to know how likely is it that I will hit any one of these price levels. And I mean, it's a classic statistical expectation where you multiply a probability function by some other function to figure out the expected value. And so in this case, we're using the probability function of stock price, is that the future price of the stock is pretty well approximated by a log normal distribution. It's a little more fat-tailed than log normal, but it's a decent way to think about it. And so what I would do is I would say, how probable is each one of these price levels? How much money do I make if I'm at that price level? So when I multiply this function by this function, I get this third graph, which tells me the expected payoff I am likely to get from each one of these price levels. And you see on the left-hand side, because I always lose the same amount of money, I don't have a lot of loss area below this zero line. On the right-hand side, I have a lot of area above it, and that's telling me that the stock option makes money. Now, why does it make money? Does it make money because of the probability function? Not really, because the probability function is basically symmetric. it makes money because of that asymmetric payoff function. It is payoff function asymmetry that is really driving the value of stock options. And so if I ask you the question, what would happen if I increase the variability of the stock price? I won't pull it out of you, I'll give you the correct answer. If I increase variability, I spread the tails in both directions. When I extend the tail on the left-hand side, it doesn't make any difference. I still have a 50% chance of losing the value of the option. When I spread the tail on the right-hand side, it goes deeper into the high payoff region, and I make more money. So when you compare two different levels of variability, here I use two different standard deviations, the blue one being the low one. On the left-hand side, the area is the same. You can't actually see that easily, but it's the same area, it's just distributed differently. On the right-hand side, there is more area. So if you had a lean manufacturing person go to an economist and they said, you know, in lean manufacturing, we have many insights on how to manage a business correctly, and one of the things we have learned is that if we minimize variability, we maximize economic outcomes. We think this truth is so important, we should bring it to the entire rest of the world and convince the whole software industry that minimizing variability will also end up maximizing their economic outcomes. The response of the economists would be to laugh in their face. They would say, you understand nothing about economics, because while it is true there are certain situations where minimizing variability maximizes the economic outcome, there are plenty of situations where increasing variability is what maximizes the economic outcome. And the point I would make on this, back up, is that it is not, I don't want to convince you that because you shouldn't be eliminating variability, you should be a good binary thinker and say, I should then maximize variability to get a good outcome. The real answer is it's when variability runs into an asymmetric payoff that you get money from variability. Variability intrinsically does not make you money. It's variability processed through an asymmetric payoff. And the implication of that is that what you want to do to your process design is you want to increase the asymmetry in the payoff functions and things. And that, just to give you a simple example, that is precisely what is being done. It's not articulated this way, but it's precisely what is being done with lean startup techniques, where you say, I identify an MVP, and then if I get a bad outcome, I pivot. I don't proceed any further down that path. If I get a good outcome, I continue to invest in it. Because what that's really doing is I say, I may have an equal probability of being on the negative tail or the positive tail of that distribution, but if every time on the negative tail I stop dumping money into it, and every time on the positive tail I continue dumping money in it, it doesn't matter whether that's a symmetric distribution. I'm going to make money on it because I've created an asymmetry in the way I process the events. So I think that's a very different view than manufacturing people have. So the key to getting better outcomes in the presence of variability is to create payoff asymmetries. I'm going to mention this in a later section as well when I talk about feedback. Next big idea is the fastest and easiest way to reduce queues is to reduce the batch size in our development process. People tend to think large batches have high economies of scale. I think this is pretty much a done issue in the world of product development, particularly in software development, because you have made massive reductions in batch size in software. I usually use the example of how people review drawings in an engineering process, where I take the example of one company that would complete 200 engineering drawings over a 10-week period and review them all in one big bang drawing review at the end of the 10 weeks. I contrast that with another company doing the same type of product who reviews drawings once every week. Every Wednesday afternoon, 1 p.m., they review whatever drawings were done in the last week. Now, note that they are doing it on a regular cadence, because if you're going to have lots of meetings, you don't want to do them asynchronously on demand. You want to pre-schedule them cadence just the way you do your daily stand-ups. It's the best way to avoid coordination. What's the difference between these two companies? Well, there's two important differences. One is you're getting feedback in average of 5 weeks after you did the drawing in this left-hand model. You're getting feedback in average of a half a week after you do the drawing in the right-hand model. So you're getting much, if you make a bad assumption about manufacturing capability, you do not embed that bad assumption in 200 drawings. You embed it in 20 drawings, you change your mind, and you make the rest of the drawings conform with manufacturing capability. Just the way in software, if you make a bad assumption about a protocol and you wait 90 days to get the test results and things like that, you embed the bad assumption in 90 days with the code. If you give people feedback 24 hours after they wrote the code, there's some chance they can remember what they were doing 24 hours ago, and they stop making the bad assumptions. So you get much higher quality when you accelerate feedback, and that's done by reducing batch size. The second important point is this red shaded area is giving you an indication of the size of the queue. The average queue in the right-hand process has dropped by a factor of 10 from the left-hand process. And so what it's doing is you're actually on the critical path for 1/10 the time. So, and make that more concretely, the next stage in this process is material planning. In this process, it's the elephant traveling through the boa constrictor. They receive a batch of 200 drawings to process at the same time. In this process, they begin and they wait 10 weeks, they do nothing for 10 weeks, and then they receive 200 drawings. In this process, 1 week into the process, they have started processing the first 20 drawings. So it's only on the critical path for 1 week instead of 10 weeks. Batch size is actually a quantifiable issue. The slogan that they use in lean manufacturing is lot size 1 is the perfect answer and things, so don't even think about it. The economic lot size equation is actually the way you calculate the correct batch size. And it was originally written up in 1913, so it's only 104 years old. It's not really new technology that I'm talking about. Although at the time the guy wrote about it in Manufacturing Management magazine. He said, most engineers do not understand the economics of lot size. Well, my son just graduated with an engineering degree a couple of years ago from UCLA and things like that, and I can say that statement is still true. You can get an engineering degree without understanding anything about the economics of batch size, because the only place we teach that is in manufacturing engineering and industrial engineering. The light has not gone off in all other disciplines. They are handling information in batch sizes, and the economics of batch size apply in every engineering discipline, including software. The way I often explain this is you're making a trade-off between holding cost and transaction cost. So let's say I'm the father in my family, and this was very 20th century, and I make the rules and things. And so I decide we're going to the supermarket too often. And I say, look, we're taking too many trips to the supermarket. I think we eat eggs every morning for breakfast. I think we should buy a year's worth of eggs on each trip to the supermarket. And so what happens? My transaction cost goes way down because we don't go to the supermarket very early, but very often. But I have to buy another refrigerator, and I have to invest money in my egg inventory, and it's constantly perishing on me. I have to buy more eggs and things like that. So it's not working so well. So as usual, we'll get feedback from my kids, and they say, Dad, this is not working. Good idea, Dad, but this is not working. And have you heard of the internet? I Googled this problem. I know what the answer is. The lean manufacturing people have the answer. You could have found it yourself if you knew how to use a computer and things. And I said, okay, what's the answer? He said, lot size 1. That's the answer. I said, lot size 1. Let me read that article because I'm not sure you know how to read. more than 500 words, once a week worth of data. And I sort of grew up reading longer articles. So I look at it and say, you know, you're right. They say lot size 1 is the answer, so change of direction, family. Holding cost has gotten very low because I only need space for 1 egg in my refrigerator, but my transaction cost has gone through the roof. I have very high transaction costs. And we're always, in all cases, we are trying to make a trade-off between these two costs. Now, I think the very interesting thing that has happened in software is if you look in the coding process, what happened is we invested a lot in test automation. We have reduced the cost of doing tests by multiple orders of magnitude, and that has made it effective to operate in very small batches of coding. Now, people have then looked and said, well, we're still doing deployment in large batches because we have a large transaction cost associated with deployment. And the DevOps people are now saying, hey, look, you know, why don't we end up doing the same thing we did in coding? Why don't we go ahead and automate the deployment workflows, drive down the transaction cost of deployment, so it is very cheap to end up deploying our product. And that is actually rippling back into the way some of the people are using agile methods, because it used to be when you talk to somebody using Scrum, they would introduce all their stories at the end of the sprint because they had a high transaction cost, and they would release all the stories at the end of the sprint. Now, I consistently run into teams who have said, my deployment process has been so automated that I can deploy in very small batches. And so they are deploying stories as soon as they're done in the sprint instead of waiting until the end of the sprint. And it's this transformation of driving down transaction costs that makes it effective to operate in small batches. And of course, the people who have fundamentally high transaction costs, like major regulatory approvals and things, if you're designing flight control software for Boeing 777, you don't want to go through type certification more than once. So they intrinsically have to use a large batch deployment on the end of the process, but they do not have to use large batches in the writing of the code. They can still use small batches inside the process. Okay, idea number 3, best way to control the cycle time of a process is to control the amount of WIP in a process. This is a diagram that I have used for like, I don't know how many years, 30 years or so. It has stood the test of time. I find that the CEO with the shortest attention span still has a sufficient attention span to have this diagram explained to them. And I'm not making fun of CEOs. They tend to be very smart people, but they don't like long explanations. So it's really good to find a short explanation that they get. So I explain to them, here's what you're doing. You're spreading your resources across 4 different programs simultaneously. You're completing 4 programs at the end of 2 years. Here's what you could be doing. You could concentrate your resources on project 1 and 2 and clear them in 1 year, and then do project 3 and 4 and clear them. And you would recognize this upper system has a WIP constraint of 4 items in process. The lower system has 2 items in process. If I'm dealing with somebody who knows the cost of delay, this is a very short conversation, because I say the cost delay on your average cost delay on your project is $100,000 a month. If you use the lower approach, then you save a year of cycle time on project 1 and 2 in time to market. 12 months times $100,000, $1.2 million. 2 of them, that's worth $2.4 million. So it's $2.4 million a year of extra profit. And so explain to me why you think it makes sense to dilute your resources across 4 different projects. Because you'll still have 4 projects done at the end of 2 years. Now, occasionally I get the response of saying, well, we like to tell our customers we're working on everything. We have a lot of internal customers, we have external customers. We like to tell our customers we're working on everything. And I always tell them, if you tell the customers you're working on everything, you need to practice full disclosure. You need to tell them, we are working on everything, but we guarantee you, you will not get it any earlier than if we were not working on it at all. In a capacity constrained system, what governs the rate at which you deliver stuff is the capacity of the system. It is not the amount of stuff you stick in the system. Starting earlier has no effect on causing you to finish early. All it does is raise the amount of WIP, dilute the resources, and ultimately it will end up slowing you down. I didn't include it. I've got another diagram to use sometimes, but this is, you need to convince people. And interestingly, the other thing I point out to them is this does not just benefit project 1 and 2. On project 3 and 4, you are pulling the trigger 1 year prior to market introduction instead of 2 years. That means you have more mature technology, you have a better, more accurate sense of what the requirements are, and you have learned from project 1 and 2. So while project 1 and 2 should obviously be the high cost delay projects because they benefit most of things, you will still benefit 3 and 4 as well. And again, assuming you know cost of delay. If you don't know cost of delay, you can't really do much rational about this. Now, more on my background. Long ago, I was in the Navy. During the Cold War, I was on nuclear submarines. We would look for other people's submarines in the middle of the ocean. We would know where they were at one moment in time. Somebody would see a periscope or hear a sound or intercept a radio signal. They could be going in any direction. The area we had to search to look for them was proportional. They could be going at a speed in any direction. So the area we had to search was proportional to velocity squared and time squared. It was much easier to find a diesel submarine than a nuclear submarine, not because diesel submarines are noisier, which is what some people reading Tom Clancy books would think. But the real issue is it's a question of speed. A nuclear submarine is traveling so fast, they reach a point where in 1 hour of elapsed time, they add an annulus of area which is larger than the area you can search in 1 hour. So if they add 40 square miles of more search area and you can only search 10 square miles per hour and things like that, it is getting less and less probable you will find it. And so what do we do to find nuclear submarines? We get something that gets to the datum really fast. So we use things like a Lynx helicopter, or what you use is a Lynx helicopter or a Nimrod plane. They don't have great sensors, but they don't need great sensors because when you get there quickly, it's really easy to find the submarine. Now, in this case, uncertainty goes up with 2 degrees with time squared because there are 2 degrees of freedom. How many degrees of freedom do you have in your product requirement? Anybody have 2 or less, things like that? And this is the issue. And I was working with a telecommunication company that did a 6-month development program in a business that traditionally had taken 3 years. They developed the product so fast, it was a highly successful product. They actually left out certain features because they were so quick to market, they didn't need all the features they originally thought they needed. It was so successful, the general manager of the business asked me, talk to the team leader, find out what he did so we can bottle this and get everybody to do it. So I went down to see him and I said, John, what do you attribute your success to? Why were you so successful on this program? And it was a co-located team. They were all within, in the same room and things. And one of the questions I asked was, how often did you hold team meetings? And he said, what a funny question. Why would we gather in a conference room to show slides to each other? We were all in the same room. I would just roll my chair over to the other desk and we'd put the issue to bed and we could get back to work. But the other thing he said, which will give you a clue that he was an engineer, is he told me, we developed the product so fast that marketing didn't have time to change their mind. And I'm an MBA and an engineer, so sometimes I root for the marketing folks. I said, John, I would have phrased it a different way. I would have said, you developed it so fast that marketing didn't have to change their mind. Because I said, in the reality in your sector in the telecommunication space is nobody can forecast requirements at a 3-year time horizon. Everybody can forecast requirements at a 6-month time horizon. The biggest thing, and it's worth noting that the majority of projects fail because they do not meet the market requirements. It's not because they don't technically, it's because they have the wrong market requirements they are designed to. That's the primary cause of failure. And that cause of failure goes up exponentially when you have long cycle times. And the interesting thing is when you look at the long cycle times, what you find is the majority of that cycle time is not, in fact, time when engineers are working. The majority of the cycle time is when work product is sitting idle because of the queues that you have on the critical path of your development program. So you just absolutely kill your ability to have good requirements when you end up having long cycle times in the process. With control, all of you are probably familiar with Kanban boards and how they work. I'll just make one little comment about it because some people will see Kanban, and this is sort of based on something I saw when I visited Dave Anderson when I was at Microsoft and things, but it's fairly generic. There's a ready queue code and ready testing that's complete. The big difference, people will see visual control boards and they'll say, sorry, what they said, isn't this what we've always done? I mean, we've used PERT charts, we used Gantt charts and things. We're using visual charts and we use them for control purposes. So what is really different about what you software people are doing today? And I tell people this is a fundamental change in the way we're thinking about controlling the system. Because on a Gantt chart and on a PERT chart, the horizontal axis was always time. What is the horizontal axis on this visual control board? It is not time. It's state. It's the state the work is in. And that changes everything. Because if I know what state occupancy is, then I know where the queue is. And the queue is the majority source of cycle time. So if I'm updating this board at a daily stand-up meeting, this is the first time we have ever had a real-time sense of where the queue is in our development process. It is completely transformational when people set up boards that show what all the work is and in each state in the process. And I would say, even if you do not have a WIP limit on a visual control board, it will be completely transformational. If you have a WIP limit, it's even better because you end up controlling the amount of WIP. But you don't even have to have a WIP limit to make a visual control board completely change the way people do their work. Okay, so control the start rate of work. I'd say there is a major management illusion where people believe the sooner they start work, the sooner they will finish. And this is just a huge misconception on the part of management. If an engineer becomes free for 2 or 3 days, I guess we have capacity to start another project, and at least we'll get some work done that we won't have to do later. The problem is the work is perishable. Anything that you have in flight is essentially a perishable item that is losing value over time. I would talk with one team at HP where when they would find a bug in their software, they would end up, first they would make the triage decision, what is the severity level, are we going to fix this? And second, they would make the dispatch decision, they would say, who do we assign this to? And they would make the dispatch decision as soon as they had made the triage decision. They would say, oh, let's assign it to the person who wrote the code originally. So when they would dispatch immediately, they had lots of bugs in process at the same time. In fact, they had so many bugs in process that they were fixing bugs in modules of the code that were no longer in the product by the time they ended up implementing the fix. And they said, there's something wrong with this process. So they still did the triage decision very quickly because you had to find the high severity stuff. But they did not dispatch everything immediately. They said, we're going to control the number of bugs we're working on at a time. Anytime we fix a bug, we never let another bug in the system. By controlling the amount of WIP they had in the process, they were controlling the cycle time. And controlling the cycle time meant that they didn't have these slow-moving projects that would become obsolete in the amount of time they sat within the system. So you basically do not want to keep your work in flight for a long period of time because you're exponentially more vulnerable to requirements change when you do that. Okay, big idea number 6. Both project and portfolio level, the sequencing of work should be based on economics. This is a diagram I use to illustrate the economic effects of sequencing. Horizontal axis is time, the vertical axis is cost or delay. Here I have 3 projects, project 1, 2, and 3. They all have equal duration, they all have the same cost of delay. If I do project 1 first, it experiences no delay. Project 2 is delayed by the duration of project 1. If the height of this rectangle is equal to cost of delay, then the area of this rectangle, let's say it's 3 months delay at a cost delay of $3 million a month, then the area is $9 million is my delay cost. So when I use the term delay cost, I'm referring to is denominated in dollars. When I use the term cost of delay, it's dollars per month. It's the rate at which delay causes that. So in the case of project 3, I'm delayed for let's say 6 months, same cost of delay. I get this red shaded area. The size of the red shaded area is the delay cost. If I do the sequence 1, 2, 3 or 3, 2, 1, the area stays the same. So what that's telling you is in the managing world, in the manufacturing world, where we have homogeneous flow, there is no money to be made by changing the sequence of jobs, which is why manufacturing people don't spend much time on prioritization systems, because there is no money in that hole. Now, go to the product development world where we have different durations and different costs of delay, then what we want to do is we want to prioritize on the basis of weighted shortest job first. The weighting is done as the cost of delay divided by the duration. You can think of that as being, how do I get maximum bang for the buck? The benefit that I get is the cost of delay that I end up avoiding. The cost is how long I block a resource. So in this case, what I'm doing is I take this weighting 10, 1, 0.1, I process in that order with job 1, 2, and 3. I contrast that with processing in the reverse order 3, 2, 1. This is actually a 96% reduction in delay cost. And this is what originally caught Ian Leffingwell's interest in SAFE, because he said, you know, you're not changing the capacity of the system, you're not changing the demand on the system, you're not changing the average size of the queue, but you're getting a 96% reduction in delay cost. There must be something to this weighted shortest job first stuff. And there is, because you're moving stuff with a high cost delay through the system faster than other things. Now, currently, well, I don't have a slot for it. There are probably easier ways to do weighted shortest job first than the current method that is being used in SAFE. Sometimes in my longer courses, I talk about a 9-box matrix that you can end up using. I don't really have a slide for doing that tonight, but I'll say I'm a huge supporter of SAFE because it's the only methodology that's paying any attention to cost of delay. I would never suggest people not use SAFE because of the way SAFE is doing weighted shortest job first, but I truly believe that 5 years from now, you're going to see that the way weighted shortest job first is done in SAFE is going to change to becoming a lot less Fibonacci numbers and a lot more economic numbers. And that is, I think, the direction it's going to be going. And I'm certainly going to be working with them to try and move it in that direction. Okay, sequencing work on basic economics. I've talked about it. Big idea number 7, feedback loops enable better economic performance in the presence of uncertainty. I used this little toy problem to illustrate the idea. Let's say I was willing to sell you a lottery ticket for $3 that would pay a $3,000 prize if you picked the correct 3-digit number. You'd be able to very quickly figure out that one chance out of 1,000 of winning $3,000 is worth $3, and that is a break-even game. What would happen if I changed this game and I said, I'm going to charge you, I'll still charge you $3 to buy a 3-digit number, but I'll let you buy the first digit, and I will give you feedback whether you have picked the correct first digit, and then you can choose whether you want to buy the second digit, and then I'll give you feedback, and you can choose to end up whether you want to buy the third digit. because in fact, this is significantly altering the payoff asymmetry in this game, which is one thing I was telling you is important. What do the economics of the second game look like? The economics of the second game is, this is the probability of spending the money. 100% chance you're going to spend the first dollar, 10% chance you're going to spend the second dollar, 1% chance you're going to spend the third dollar. The average payoff in the second game is $1.89. The average payoff in the first game is 0. Now, where is that extra payoff coming from? Is it coming from, did I change the size of the prize? The prize is still $3,000. Did I change the probability of picking the correct number? I still have one chance out of 1,000 picking the correct 3-digit number. Did I change the cost of playing? It's still $3 in my 3 digits. Somebody trained in finance would say the difference between the second game and the first game is the second game has shutdown options. You have put 2 shutdown options in the second game, and the value is being added by the presence of these shutdown options that allow you to shut down an unproductive bet. Anything with the wrong first digit is not going to end up paying off for you. So shut down all investment in that particular bet. And my view of the world is a lot of people treat product development as if it's a horse race where I try to pick which horse is going to win and I place my bet and then I watch and see what happens. My view of the world is product development is a horse race where you can move your money after the horses have started running. So as the horses run down the track, that changes your expectation of which horse is going to win. And when the customer originally told you this feature is really important, and you're halfway through the development program, and he says, I don't care about this feature anymore, you really ought to be smart enough to say, I need to take money off that feature, and I need to move that money to the feature that he's saying is important to me. Because the problem is the world changes on you, and you're just flushing money down the toilet if you end up investing in stuff that is no longer important to customers. Okay. So that's the importance of celebrating feedback, and these are the ideas I talked about. I guess I'm pretty close to making time. I compressed a lot of stuff in, obviously left a lot of stuff out, and I'm very open to answering any questions that would logically occur from all of my omissions.